Okay, what are these people doing? Okay, they're working, right? All right, some people, some of you in here might think this is working. Okay? All right, in physics, okay, we think work jobs. Okay, in physics it means something different. That's what we're going to go over today. And we're going to relate it to stuff that you already know. And that's one of the cool things about physics is it's all connected. Okay, even electricity stuff, all right, that we'll study at the end of the year. It's connected to stuff we're doing right now. Okay, so how do we define work? Here's what we want to conquer today and in the next couple periods, okay? We want to be able to define these words. Today, just these. We want to know the units of each of these. And they're all connected. We want to know how this is connected to this and how both of these are connected to energy. And of course, do calculations with them. All right, that's what we're doing. Okay, so we're going to start by doing work. All right, we'll start with an equation, force times distance. Okay, we'll explain what it actually is in a second, but I want to get you guys a couple more things down on paper. Okay, so let's talk units. We know the units of these. We've got newtons, we've got meters. We're pretty good at that already. Okay, and so a unit we could say for work is the Newton meter. Okay, however, scientists, we don't really use that very often for work. You guys can ignore that. That's just the Newton broken down into MKS. This is what we actually will be using, okay, when writing our answers for work. Okay, it's measured in joules. All right, where have we used that before? Okay, energy. How many of you took chemistry? What was measured in joules? Okay, calories and joules are both energy measurements. All right, specifically in chemistry, you guys studied heat, right? Okay, so we do a little reaction over here, all right, with Miss Timmer, and it creates some heat, right? Something warms up, okay, and we called that Q, and it's measured in joules. There's lots of different types of energy. Okay, now work is not really energy, but work involves changing energy. So here's some examples, okay? All right, if I take this football and I move it from here to here, did I exert a force? Did it move a distance? Okay, so I did some work and now it has more of what kind of energy? Potential energy, which you've all studied in like 8th grade or something like that, okay? All right, here it's got some potential energy. Now it has more because I did that, okay? All right, now if I take this and I exert a force over a distance here, okay, maybe that was like a meter of distance and I exerted some amount of newtons, okay, I did work and it gained what type of energy? Kinetic energy, the energy of motion, okay? Now once it left my hand, what was in control? Gravity's in control, it's in free fall, okay, and gravity is exerting a downward force over some amount of downward distance, and that's going to increase the kinetic energy as well, okay? So that's what we're going to do with this. We're going to talk about how this is connected to energy, okay? In fact, this equation right here is not really that helpful until we start connecting it to energy. Then it can do some cool things for us. Okay, so I just took a picture of this because I didn't want to stand here and hold Clyde, okay? You guys know Clyde, right? All right, our big train track over here, 66 pounds. I didn't want to do that 3 times today, okay? So if you do that, all right, are you doing work? If you hold that out there, would that be considered a workout? Okay, maybe so, all right, even if you just held it, that might be considered a workout, but let's do the math here. Okay, look at this. There's the equation. here's pounds to newtons. Okay, 66, there's 4.45 newtons in a pound. Okay, so that's 294 newtons, but look, the distance is 0 for just holding it out there. Am I changing its potential energy by holding it? No. Am I changing its kinetic energy? No. So there's 0 work done here in this situation. All right, 0 joules of work done. Okay, now back to this just for a second though. Okay, so if there's no work done, why is this difficult to do? Okay, are we spending some energy still? Yes. All right, you are taking chemical potential, calories from lunch, all right, and it's being converted into what type of energy? Hint, you would start to sweat if you did this. So where's it going? Heat, okay? And in physics, heat's kind of like wasted energy, all right, unless you're trying to like heat up water and create steam and like spin a turbine in a power plant. Okay, so it's just kind of wasted energy. It's not actually changing the potential or kinetic. Okay, here's the equation with a little bit more detail. Okay, here's what's going on. The arrows mean vectors. So the direction of forces matter. The direction, really this is displacement and not distance. Okay, the direction matters. And in the cosine theta, that's this. It's the angle between the force and the distance. Okay, so we're going to deal with that here. Okay, so you guys remember all the problems where we're like pulling boxes along and friction is resisting us and all that? Okay, we did in quarantine. All right, let's make it a little bit more interesting. Let's say we've got a skier right here. Did you guys know there's like surface lifts at ski areas where you like hold like a pole and it pulls you along the ground? You guys know what those are called? It's called the T-bar. Okay, and you're sitting on like this, it's usually like a disc and it's pulling you along. So here's a skier. Okay, they're riding on this thing, okay, and they're being pulled along by like a lift system. Okay, you don't actually go up in the air, you just skid along on the snow. Okay, so this is exerting a force. All right, we could call it tension, we could call it force applied. All right, and let's say this particular part is flat ground. Okay, so we've got some distance we're going to go here, and it would work on a slope as well. All right, and since we've got an angle, you know we're going to have to do some trig, you know it. Okay, so let's call this force applied. What would we call that green component there? FA. Okay, we call it FAX. Yep. We can also call it FA cos theta, right? Okay, so force applied times the cosine of theta and force applied times the sine of theta. Okay, so let's look at this. One more thing here. Only the parallel component of force does work, okay? And that's because it's the parallel component to this distance that's actually going to move the skier. The vertical component, that's just reducing the normal force, all right? But is the skier actually being lifted vertically off the snow? No, so there's no work done vertically, all right? It's only horizontal. So if I want to find the work in this situation, I do work is equal to FA cos theta times the distance traveled. Can we see that this is the same as that, just rearranged? Okay, parallel component. We'll talk more about that in the other YouTube video right below there. Okay, a couple more examples. Let's say we've got a forklift, and it's got this big weight of 1,000 newtons, and it's just going to kind of roll over here, slow constant velocity. Okay, it's not accelerating or anything, it's just kind of going slow. And let's say it goes 6 meters. Okay? To hold this weight up right here, its force had to be upward. So we've got a force that is up to hold that weight. Okay, it's not like skidding it across the ground. If it was doing that, we'd be doing something like this over here. Okay, so the force is up and the distance is in that direction. Okay, so in this case, 0 work is done. Why is that? We're going to need some calculators today anyway. Let's get them out just to prove a very simple thing here. Okay, so what is the angle between the distance and the force? What do we got? 90 degrees, right? Perpendicular. What is the cosine of 90? It is 0. Okay, if you plug it into your calculator, you can prove it. Very easy. Cos 90 equals 0. Okay, 0 work done. Okay, and that would be this plugged into the equation. Oh, look, here's some TikTok for you guys. A student sent me this. Okay, see if you can find any problems with this TikTok.
Wow, this is great pay for not doing any work. Alright, so the joke is actually really funny.
Did you guys think that was funny?
The equation for work is work equals force times displacement cosine of theta. And in this scenario of the waiter holding up the tray at a 90-degree angle, as shown here, that would mean that cosine of theta would be 90. So, as everyone knows, cosine of 90 is equal to 0 degrees, right? So now, since it's 0 degrees, anything that force and displacement is equal to will equal 0. So, in conclusion, the waiter is doing 0 newtons of work on the plate. Thus the joke, wow, this is great work for doing no pay because he's doing no work.
There you go. There's your TikTok for the day. Okay, any problems with that? I mean, I'm proud of the guy. He's doing physics on TikTok. I can't knock him for that. Okay, yeah, besides that, yeah. Anybody catch it? Coulter? Okay, that doesn't matter though, all right? He's talking about the vertical stuff. Great pay for doing no work. That part's all good. That part's fine. Okay, it was his math at the end. What was the 0 measured in? The degrees was 90, right? Okay, what's work measured in? Joules, okay, not newtons. Okay, that's what we were talking about earlier. We really need to keep our units straight. Okay, work, joules, force, newtons. Not again. Okay, how about this scenario? All right, we're going to actually lift the crate. Okay, what direction was the force that the forklift used? Vertical, up. Okay, and so is the distance. So they're working together, all right, same direction. All right, calculate the work done in this situation. And you probably don't need a calculator, right? Okay, what is the angle between these two? 90 is if they're doing this. Okay, 180 is if they're doing that. I feel like I'm doing a sweet dance move. Okay. 0, all right? These lines are parallel in the same direction, okay? 0 degrees. So we just have to do FD cos 0. What's cos 0? Cos 0 is 1, okay? So it's 1,500 joules of work, all right? Okay, now here's your lab we're going to do in just a second. You're going to figure out your work done. You're also going to figure out some other stuff. Okay, but we're gonna go run stairs today, guys. Were you ready for a workout today? No pun intended. Okay, we're gonna run stairs. We might do some push-ups. Okay, so get ready. All right, there she goes. You don't have to run them one-legged. Okay, her own weight was what she had to overcome to get to the top of the stairs. She had to use an equal force to her gravitational force. All right? Which distance should we use to calculate the work? We got two distances here. Okay, her force was up, so we have to use the up distance. Okay, and by doing that, you've taken care of the degrees. All right? Here would be the degrees, down there is a 3, 4, 5 triangle, so we could figure it out really easy. All right, but we just use the vertical height with the vertical force, and so the answer would be 1,800 joules. Okay, if you're going to do a bench press, let's say you lift these plates a 1/2 meter, and they weigh that. Okay, you would just simply multiply that, and you'd be doing 147 joules per lift, all right, just for one lift. Okay, today the extra credit in the lab is push-ups, all right, so very similar to this right here. Okay, I actually used to live in Point Loma, hence the palm trees right here, and there's a grocery store right here that I used to go to, and I always thought it was funny because these guys would like go up the escalator into the 24-hour fitness. Is that funny? I mean, it's like they could go up the stairs and warm up a little bit, but no, they're going to just sit there and ride the escalator. I don't know. How much work are they doing? 0. Okay, what's doing the work? Okay, motors can do work too. Okay, we're going to have a race. These guys have the same amount of weight. Okay, who did more work? Good answer. Okay, they did the same amount of work. Look at the equation. Does it have time in it? No, work is not dependent on time, but power is. Okay, next concept. Power is how quickly work gets done. Okay, that's one definition for it. Okay, work over time. Sometimes we'll need to do this. To get the work, we'll have to do the work equation, and then we'll divide by time. Units for power. How many of you have heard of this unit before? All right, we got watts. What are we usually doing with that? We're usually doing like electricity, light bulbs, and stuff like that. Okay, today you're going to figure out the wattage that you operate at when you're walking and when you're running. Okay, so this applies to more than just electricity. And we will, later in the spring, apply this to circuits and light bulbs and all that stuff. Okay. Definition of a watt. Okay, let's put this down in our notes. Here's how we abbreviate it, capital W. 1 watt is equal to 1 joule every 1 second. Okay, so if we're spending energy, like with those little light bulbs on the ceiling, they might be like 3 watts. Okay, those little string lights. That means that every 1 second, they require 3 joules of energy to put out that much light. All right, we'll talk about light bulb efficiency and all that later. That's James Watt. We won't worry about him. Okay, so we're going to go now and we're going to figure out the wattage we can operate, and we're also going to figure out our horsepower. Okay, so that's the lab today. Let's turn to that lab.